The universe is 13.8 billion years old. We know what happened 1 second after it began, when temperatures were around 10 billion degrees. We know what happened in the minutes after that, the hours, the millions of years, but the actual moment of creation? Yeah, that one's a problem. The Big Bang singularity. Here's what most people think the Big Bang singularity is. The moment everything started. A tiny dot that exploded. The cosmic birthday. But that's not quite right. The singularity is what happens when you take general relativity, Einstein's theory of gravity, and run the math backwards. You rewind the universe and everything gets denser and hotter and more curved until eventually the equations spit out infinity. Infinite density, infinite curvature. That's not a measurement. That's a math error. When your equations give you infinity, that usually means your theory stopped working, not that reality broke. It's kind of like dividing by zero on a calculator. The calculator didn't discover a new number, it just hit its limit. So scientists genuinely debate whether the singularity is physically real or just a sign that classical gravity can't handle the extreme conditions near t equals 0. A theory of quantum gravity would probably replace the singularity with something else entirely. We just don't have that theory yet. The most famous moment in cosmic history is also the one we understand the least. So let's move past it and get to what we actually know, in order, starting with what happened in the first fraction of a second. Cosmic inflation, so the universe exists, great. But here's a weird problem. When we look in every direction, the cosmos is almost perfectly uniform in temperature and density. Regions billions of light years apart that never could have been in contact with each other somehow ended up nearly identical. That's suspicious. The leading explanation is that right after the Big Bang, the universe went absolutely unhinged. In a tiny fraction of a second, space itself expanded exponentially, roughly 50 to 60 e-foldings, which means it doubled in size over and over and over again faster than you can process this sentence. That's called cosmic inflation. It stretched everything so violently that any initial lumpiness or curvature got smoothed out like wrinkles on a balloon being blown up to the size of a continent. But it also seeded tiny quantum fluctuations into the fabric of space. Those fluctuations eventually became every galaxy, every star, every planet, including you. CMB data backs this up beautifully. The scalar spectral index sits at about 0.97, right where inflation predicts. The upper limit on primordial gravitational waves is pinned below 0.06 for the T-NIS or to scalar ratio, and some models predict signals as small as 10 to the power of -7, so faint we may literally never detect them. But here's the honest part. Inflation is not one theory. It's a family of models and the actual particle physics driving it, completely unknown. The energy scale could be anywhere from 10 to the 16th to 10 to the 19th giga-electron volts, depending on who you ask. It explains the data beautifully, but it fits is not the same as we know what caused it. So what did inflation leave behind? A universe full of hot, dense plasma, and no atoms yet. Nucleosynthesis. So the universe is a few seconds old, unimaginably hot, and basically functioning as the largest nuclear reactor ever exist. Protons and neutrons are slamming into each other and fusing into heavier stuff. First deuterium, then helium-3, then helium-4, and tiny traces of lithium-7, and then, about 5 minutes in, it's over. The universe cooled too fast for anything heavier to form. 5 minutes. That's less time than it takes to microwave a frozen burrito, and in that window, the chemical composition of the entire observable universe was basically locked in. Roughly 75% hydrogen, about 25% helium by mass, and trace amounts of everything else. That's it. That's the recipe. Now here's why this matters. We can actually test this. There's a number called the baryon to photon ratio, which is basically how much matter exists per photon in the universe. You measure it by comparing predicted deuterium to hydrogen ratios against real spectroscopic observations of ancient gas clouds. Clouds so old they're basically unchanged since the beginning, and the predictions match really, really well. This is one of the earliest direct observational tests cosmology has, and it holds up. One wrinkle though, lithium-7 consistently shows up at lower abundances than the models predict. That's called the cosmological lithium problem, and nobody's cleanly solved it yet. Could be measurement issues, could be stars processing it away, could be genuinely new physics. We don't know. But the rest of the ledger, rock solid. So the universe has its ingredients. Now it just needs to cool down enough to do something with them. Cosmic microwave background. For about 380,000 years after the Big Bang, the universe was basically a hot, foggy mess. Photons couldn't travel anywhere without slamming into free electrons. Light was trapped. But as the universe expanded and cooled, something clicked. Electrons finally slowed down enough to bind with protons and form neutral hydrogen. That's called recombination. And for the first time ever, light could travel freely through space. That ancient light is still here. It's everywhere, filling the entire universe right right now, at a temperature of 2.7255 Kelvin, plus or minus 0.0006. We call it the cosmic microwave background, or CMB, and it is not just some faint leftover glow. It is the single most important dataset in all of cosmology. The Planck satellite mapped this light with absurd precision. From a 13.8 billion year old afterglow, we extracted the Hubble constant at 67.4 plus or minus 0.5 kilometers per second per megaparsec, total matter density at 0.315, spatial curvature consistent with a perfectly flat universe, an upper limit on neutrino mass of under 0.12 electron volts, and the number of effective relativistic species at 2.99 plus or minus 0.17, which is almost exactly the standard model prediction of 3.046. That means leftover baby light from the universe independently confirmed that there are three families of neutrinos. Particle physics verified by a photograph of the sky, every major number in modern cosmology, dark matter density, dark energy's equation of state, inflationary parameters. Like all of it runs through the CMB, it's the Rosetta Stone of the universe. But here's the thing. After recombination, the lights went out, literally, the dark ages. So the CMB fires off in every direction, the universe's first and last flash of light for a very long time, and then nothing. For roughly 200 million years, the universe was completely dark. No stars, no galaxies, no light sources of any kind, just a vast, slowly cooling fog of neutral hydrogen and helium expanding into more of itself. If you could somehow float through it, you'd see absolutely nothing. Not darkness like nighttime, where there's a moon or a streetlight somewhere. Darkness like the concept of light hasn't been invented yet. The physics here is actually pretty simple. Neutral gas cooling down, gradually clumping together under gravity. That's it. No fireworks, no drama. Just the slow, silent beginning of structure, tiny density differences, barely anything, starting to pull matter together into clumps that won't become interesting for millions of years. And that simplicity is exactly what makes the Dark Ages scientifically valuable. Because the background is so clean, so featureless, any weird energy injection, say from exotic dark matter particles annihilating each other, would stick out like a flashlight in a cave. Scientists are working on detecting the 21 centimeter radio signal from all that neutral hydrogen, which would let us map this area directly. No clean detection yet. But when it comes, it'll be like turning the lights on in a room nobody's ever seen. So what finally broke the silence? Ionization. For about 200 million years, the universe sat in total darkness. No stars, no galaxies, no light sources of any kind. Just a vast cooling fog of neutral hydrogen drifting through black emptiness. That's the longest night there will ever be. And then, something ignited. The first stars formed, and they were almost certainly monsters. We're talking hundreds of times the mass of the sun, burning so hot and so bright, they flooded their surroundings with ultraviolet radiation. That radiation was intense enough to rip electrons off the neutral hydrogen atoms nearby, turning them back into ionized plasma. The same stuff the universe was made of before recombination. Basically, the universe was running the CMB process in reverse. This didn't happen all at once. It started in pockets, little bubbles of ionized gas expanding outward from wherever stars were forming, gradually merging, spreading, eating through the neutral fog like holes burning through a sheet of paper. Over hundreds of millions of years, those bubbles connected until the entire intergalactic medium flipped from neutral back to ionized. That process is called reionization. Now, what exactly drove it, whether it was mostly those giant early stars, the first small galaxies, or actively feeding black holes, that's still debated. The honest answer is we don't have the detailed observational data to pin it down precisely yet. But the big picture is clear. The universe went dark and then it lit up permanently. So now we've got stars, we've got light, we've got ionized gas everywhere. Time to build something bigger. Large scale structure. Zoom out far enough and galaxies aren't scattered randomly. They're arranged along enormous filaments connected at nodes and separated by vast empty voids. The whole thing looks like a cosmic sponge or a neural network stretching billions of light years in every direction. And this structure didn't come from nowhere. It grew directly from those tiny quantum fluctuations that inflation planted in the first fraction of a second. Microscopic wrinkles stretched to cosmic scales, slowly pulling matter together over billions of years through gravity. That's the cosmic web, but we can actually measure this with hard numbers. In the early universe, pressure waves rippled through the hot plasma, kind of like sound waves in air. Those waves traveled a fixed distance before the universe cooled enough to freeze them in place, leaving a preferred spacing between galaxy clusters. That's called baryon acoustic oscillations, and they act as a cosmic ruler. So at SDSS measurements at a redshift of about 0.15 report, a distance measure of 4.51 plus or minus 0.14 in standardized units. That's a real physical yardstick baked into the universe itself. Planck gives us the initial conditions. A matter density of 0.315 and a clustering amplitude, sigma 8, of 0.811. From those starting numbers, we can predict how much structure should have grown by now. SDSS growth rate measurements give F sigma 8 of 0.53 plus or minus 0.16 at that same redshift, which mostly agrees with predictions. Mostly. There's a small persistent tension between how much clustering the CMB predicts and what surveys actually observe. It's not a crisis, but it's not nothing either. Historically, discrepancies like this either vanish with better data or crack open entirely new physics. So what exactly is doing all that gravitational pulling? Dark matter. About 27% of the universe's total energy budget is matter. Planck puts the total matter density at omega m equals 0.315 plus or minus 0.007. But here's the thing. Only a small fraction of that is baryonic, the protons and neutron stuff that makes up you, me, stars, planets, and everything you've ever touched. The rest is dark matter. It doesn't emit light, doesn't absorb light, doesn't reflect light. It just sits there, gravitationally, being heavy and invisible. And this is not a guess. Without dark matter, the CMB power spectrum doesn't work. The growth rate of large-scale structure doesn't work. Galaxy rotation curves don't work. Your gravitational lensing observations don't work. You'd have to break 4 completely independent lines of evidence simultaneously to get rid of it. That's not a hypothesis with shaky legs. That's a load-bearing wall. Now, you might think, what about neutrinos? Those are weird and hard to detect. Fair. But Planck constrains the sum of neutrino masses to under 0.12 electron volts. They're way too light and way too fast. Dark matter needs to be cold, slow, and clumpy. Neutrinos are none of those things. So what is dark matter, honestly? We don't know. We know it's non-relativistic, non-baryonic, and non-luminous. We can map its gravitational behavior with stunning precision, but direct detection experiments have found nothing. No confirmed particle, no signal. We know exactly how it behaves and have absolutely no idea what it is, which is, to put it mildly, frustrating. But frustration doesn't change the math. And the math says about 85% of all matter in the universe is something we cannot see and have never directly detected. So what about the other 68% of the energy budget, the part that isn't matter at all? Dark energy. So dark matter is the stuff we can't see that holds everything together. Dark energy is the stuff we can't see that's tearing everything apart, and there's way more of it. In 1998, astronomers were studying distant supernovae, basically using exploding stars as cosmic measuring tapes, expecting to find that the universe's expansion was gradually slowing down. Gravity pulls stuff together, so expansion should be losing steam over time. That's what everyone assumed. But the data said the opposite. The expansion is speeding up, like something is actively pushing space apart, and whatever it is accounts for roughly 68% of the total energy content of the universe. That something is called dark energy. Now here's what we actually know about it. Planck's measurements give dark energy an equation of state parameter of W equals negative 1.03 plus or minus 0.03. That's almost exactly negative 1, which is the value you'd get from a cosmological constant, Einstein's lambda, representing a fixed energy density built into empty space itself. Space just has energy, always, everywhere, the same amount per cubic meter forever. And because Planck also measures the universe's spatial curvature at basically 0, consistent with a perfectly flat universe, that means expansion doesn't just continue, it accelerates indefinitely. A tiny positive cosmological constant mathematically rules out the universe ever collapsing back on itself. But here's the problem. If dark energy really is a cosmological constant, quantum field theory predicts its value should be roughly 10 to the power of 120 times larger than what we observe. That's not a rounding error. That is the single worst prediction in the history of physics. We know exactly what dark energy does. We have no idea what it is, and no idea why it has the value it has. So how does all of this fit together, and does any of it actually agree? The Hubble tension. So we've got this number, the Hubble constant, that tells us how fast the universe is expanding right now. Measure it from the CMB, the baby photo of the universe, and Planck gives you 67.4 kilometers per second per megaparsec. Clean number, tight error bars. Beautiful. Now measure it the other way. Use nearby Cepheid variable stars to calibrate distances, then use type 1a supernovae as standardized cosmic mile markers to measure expansion directly. You get roughly 73, not 67, 73. That's called the Hubble tension. And it's not a small disagreement. The gap between those two numbers sits at about 5 sigma. In physics, 5 sigma is the threshold where you stop saying, that's weird, and start saying this is a discovery. 5 sigma is what they required before announcing the Higgs boson. This is not a rounding error. This is not one team being sloppy. Both measurement pipelines have been independently checked, cross-checked, recalibrated, and refined for years. The numbers still disagree, so either someone is making a mistake they can't find, some subtle systematic error hiding in how we calibrate cosmic distances, or the standard model of cosmology is missing something. Maybe the universe genuinely expands at different rates depending on when and how you look at it. Maybe there's new physics lurking in that gap. Right now, nobody knows which one it is, and that's what makes this the single hottest open problem in cosmology. Two rulers, both trustworthy, both giving different answers, which raises a bigger question. If the model works this well but still cracks under pressure, what happens happens when we look at where all of this is heading, the heat death. So if dark energy keeps doing its thing and expansion continues forever, how does the story end? Not with a bang, not with a dramatic collapse, with silence. The second law of thermodynamics says entropy always increases. Everything trends toward disorder, toward equilibrium, toward a state where no temperature differences remain and no usable energy exists to do anything. Stars burn through their fuel and go dark, the last embers cool, black holes, those seemingly eternal monsters, slowly evaporate through Hawking radiation. Stellar mass black holes take roughly 10 to the power of 67 years to vanish. Supermassive ones, the kind sitting at the centers of galaxies, take about 10 to the power of 100 years. Recent calculations suggest even white dwarfs evaporate via similar processes in around 10 to the power of 78 years. Let's put that in perspective. The current age of the universe is about 13.8 billion years. That's roughly 10 to the power of 10 years. The time it takes for a supermassive black hole to evaporate is 10 to the power of 100 years. The entire history of the universe so far, everything we've talked about in this video, is effectively zero on that time scale. A rounding error of a rounding error, and after all of that, what's left? A vast, cold, featureless void. No gradients, no structure, no processes, just particles drifting apart in perfect eternal equilibrium. The universe doesn't die screaming, it just stops having anything left to say. Now, there's a caveat. Standard thermodynamics applies cleanly to closed systems in equilibrium, and the universe is expanding. Gravitational entropy remains poorly defined and is still an open theoretical problem. Heat death is the best supported end state, but applying it rigorously to cosmology is not as tidy as the popular version suggests. Still, assuming current physics holds, this is probably how it ends. So quietly, but not everyone agrees the universe goes gently. The Big Crunch versus the Big Rip. So how does it all end? Turns out the universe's entire fate comes down to a single number. W, the dark energy equation of state parameter. Think of it as a dial. If W equals exactly -1, dark energy is a cosmological constant, expansion accelerates forever, and you get the heat death we just talked about. Perpetual cold silence. If W drifts above -1, gravity could eventually win. Expansion slows, stops, reverses, and the entire universe collapses back into a singularity. That's called the Big Crunch. Poetic, right? Everything ends the way it began. But here's the thing. Current data really does not like the Big Crunch. A cosmological constant, even an absurdly tiny one, mathematically prevents recollapse in standard general relativity, and the observed acceleration of expansion pushes firmly against it. The crunch isn't impossible in pure logic, but the universe is not cooperating. Now, if W drops below -1, things get wild. That's phantom energy, and it leads to the Big Rip. In this scenario, dark energy doesn't just push things apart, it gets stronger over time. For an extreme toy model case where W equals -1.5, calculations put the Big Rip at roughly 22 billion years from now. Galaxy clusters start breaking apart hundreds of millions of years before the end. The solar system disintegrates months before, and atoms themselves get shredded in the final fraction of a second, everything that exists torn apart from the inside out. So where does W actually sit? Planck measured it at -1.028 plus or minus 0.031. That's consistent with exactly -1. Observational bounds from galaxy cluster measurements span roughly -0.907 to -1.075, which technically still allows either side. But the best fit strongly favors W equals -1. No rip anytime soon, probably just the long, cold silence. The universe began at a singularity we cannot observe, inflated for reasons we cannot fully explain, built every galaxy from quantum noise, and will end in a way that depends on a number we haven't measured precisely enough to be certain about. That is cosmology. Extraordinary precision on most fronts, and a few stubborn numbers that still hold the whole story hostage. If you enjoyed this video and want to see more, click the video on the screen now.